Let me go ahead and start the recording. All right. So go ahead and get started. People can pop in whenever. So obviously we've been working with electric fields and charges and Gauss's law to calculate fields, and you touched a bit on potential energy, but now we want to actually talk about electric potential. So Jenny, what's your best description of what electric potential is?
I guess in general, potential energy is, as far as I remember from middle school, stored energy.
That's potential
available energy, I guess.
Yeah, so that's potential energy, and that's a pretty good description. But we're not talking about potential energy, we're talking about electric potential. It's a bit different. So potential energy is what you guys were doing a bit last week and the week before. I think last week. But electric potential. So unit 10. What's the sort of like the best description of what electric potential is? How's it going, Nathaniel?
Hey, can you hear me?
Trying to figure out, Nathaniel, what's your best description of what electric potential is? Not potential energy, but electric potential.
Are you asking me?
Yes.
So what electric potential is?
Yeah.
Let's see. So electric potential, my understanding is, well, first and foremost, it's measured in volts. So, geez, I'm not sure how to explain it. I guess just the interaction of charges at a given point.
So the interaction of charges at a given point. That's pretty good. Anyone else had anything else to say? Anything else to add? Zach, you got anything to add? Go ahead, Nathaniel.
Rather than charges, maybe energy?
You saying charges energy? It's not quite.
Like the energy of the charged particles.
So that would, that would be more the potential energy rather than the potential.
Right. So the potential would just be like, I guess the interaction of these charges, but then like the electric field is present. So also how they interact with the electric field.
Yeah. There's not really a specific answer I'm looking for here, because the best way to describe it is it's some sort of way of. It's an additional way of quantifying how charges and fields and whatnot interact with each other. And so what is it mathematically? What is electric potential mathematically?
Like the equation?
Yeah.
I guess the change, well, it would just be the potential energy over the charge. The change in potential energy over the charge. No. Yeah. Over the charge.
The change in potential energy over the charge?
Like delta U over Q is what I mean.
Delta U over Q, yep. So it's, or at least that's the change in potential energy. The change in potential would be the change in potential energy divided for a charge. So, so the potential of a charge is equal to the change in potential is the same is equal to the change in potential energy of the charge divided by the charge itself. And so what's another way of defining electric potential mathematically in terms of an electric field?
Would it be like KQ over the distance?
So you're saying KQ over a distance r? And so do you know how we actually derive this KQ over R?
I believe so. So I think, do we have to kind of relate it to the work done? Mm-hmm.
I guess you could think of it like that. But there's another equation from your equation sheet I'm looking for. Go ahead, Jenny.
I thought it was from the potential energy is K Q times Q over R.
Mm-hmm. I mean, that's just connecting these two equations here, right? Because we have potential energy is K times Q1 times Q2 over R, and we divide by the one charge, and we get KQ over R. I'm looking for a certain equation. It's an integral.
Oh.
Here's one like E times DL.
Exactly. So what is it? So the change in potential is equal to
the negative integral
yes, negative integral.
of E, I think that's electric field, times DL.
Yep, exactly. So it's the change in potential energy, or the change from the way he uses it is from A to B, is the integral from the negative integral from A to B of E dot DL. And essentially it's a line integral. You guys don't have to understand the whole workings of line integrals because it just simplifies really easily in all the examples we'll see. But this is effectively the way that we describe electric potential mathematically. And we actually use this equation here to be able to derive the other stuff up there. So that's sort of what electric potential is. It's very simply mathematically the integral of E dot dl, and it's a way to describe how charges interact with one another. Does anyone have any questions about that? I'll admit electric potential is one of the things that I find is most difficult to conceptually grasp, but the math makes a lot of sense and actually works out really nicely. And I think the best way to get comfortable with it is to go ahead and work on some examples. So let's go ahead and hop into an example here. So we're going to have a uniform sphere of charge. It has a charge density, and it's going to be surrounded by a conducting shell that's uncharged. And we're going to go ahead and define our electric potential to be 0 at infinity. Why do we have to define the electric potential somewhere? Does anyone know why we have to specifically define a point where it's 0?
We need to do that because we need to be able to calculate at a certain point, we need to know at least one of the other point, right?
Yeah, exactly. So basically, when we're calculating a potential, when we calculate V, a potential, it's like calculating a potential energy where there's not, it's all about changes in potential or changes in potential energy. We have to have some sort of reference point where the potential is 0. And conveniently, in most examples, we just select some point super far off at infinity to be 0. Some other examples, you can't do that, so you just have to have the potential as a difference between 2 points. But for most of the examples you'll see, just define infinity to be 0. So we're going to define the potential to be 0 at infinity. So we have our charge density. Let me go ahead and actually yoink this image. I don't want to redraw it. We go ahead and put it into Paint. Boom, there we go. So let's go ahead and first off, let's go ahead and take 2 minutes. I want you guys to sketch what the electric field is going to look like for this charge distribution. So it's a sphere of charge surrounded by an uncharged conducting shell. And draw what the electric field is going to look like, and also what are the equipotential lines going to look like. Go ahead and take 2 minutes and we'll go over it. Also, if anyone has not already put their campus IDs in the attendance form, if you could do that, that would be greatly appreciated. Thank you. All right. So, what's our electric field going to look like for this charge distribution? What direction are our electric field lines going to be going?
Put a point inwards.
Inwards? So like radially inwards?
Mm-hmm.
Yep, exactly. So our electric field lines are going to point radially inwards, something like this. Is there going to be an electric field in this area here?
No.
No. Why is that?
Because it's a conducting shell.
Exactly. Conductor, 0 electric field. So our electric field is going to look something like this. Obviously, I'm not drawing the arrows, to indicate, like, obviously our arrows would be bigger towards the center and smaller further out, but I'm not going to bother with that because it'd be annoying to draw. So electric field is going to be radially inward because it's a negative charge in the center. So now, what are equipotential lines? What is an equipotential line?
As the way I think of it is just like circular lines that represent the potential, like at certain ranges.
So can you elaborate? What do you mean the potential at certain ranges?
So like depending on where, so they're like circular lines, right? Or whatever. Essentially, these equipotential lines either are close to each other or they're spaced apart depending on the charged particle. But essentially, they just represent what the potential is at that given equipotential line.
So what you're saying is along one single equipotential line, the potential's constant. Is that what you're saying?
Yes.
Exactly. So equipotential line is a line where the potential is going to be constant. And so now you said it was something going to be circular. Well, that's true for this example, but is the equipotential line going to be circular for every example you see?
No.
No. What's specifically can you always do to know what your equipotential lines are going to look like? Like, what do they look like relative to the electric field lines?
They're perpendicular?
Yep, exactly. They're always perpendicular to the electric field. So, example, up here, the electric field is going straight downward. Our equipotential line there is going to be perpendicular to it. And in this case, perpendicular to the electric field, it's going to look something like this. It's just a circle, or in this case, 3 dimensions, a sphere. So we have an equipotential sphere. And then as we get inside, we have more equipotential lines in here. and they actually end up getting closer and closer and closer together. Because why do they get closer and closer together versus out here they're further apart?
That was my question too.
Anyone else want to help Nathaniel out?
It's closer together when the electric field is stronger.
Exactly.
Is that what you're asking? Okay.
Yeah. So the closer together our equipotential lines are, the stronger our electric field, and vice versa. So, go ahead.
Does the sign of the charge matter?
No, we're just worried about the magnitude of the electric field.
Right.
So if this was a positive charge, and all our electric field lines were going outward, it'd still be the same thing. We'd have more equipotential lines closer together near the center.
Okay.
And so another thing I want to ask before we go into the next part is, what is the electric potential going to be bigger, or more positive, or more negative? Is it going to be smaller or more negative as we approach the center? Is the electric potential increasing, becoming more positive, or decreasing or becoming more negative as we go towards the center?
Decreasing.
Why is that?
Because at the center it's supposed to be 0, right?
We defined it to be 0 at infinity, right?
Right.
So is it going to be negative at the center, or is it going to be positive?
Not sure.
You said it was negative, right?
Oh, I said not sure.
Oh, okay. Well, I'll give you a
One of the
hint.
examples we did in class, or maybe it's from one of the class questions. Usually, like as it gets closer to the center, it would decrease. But that's was one of my questions. Like, if the volts is increasing, or if the potential is decreasing as you get closer to the center, like just that whole concept, I don't understand. Like you said initially that the stronger the electric fields, the higher the potential, right?
I didn't. No, sorry. It's not. The potential doesn't get higher. There's more equipotential lines closer together. So, I mean, whether these potential lines are like for 50 volts, 55, 60 volts, or if it's negative 50, negative 55, negative 60.
Mm-hmm.
So is it going to be positive or negative in this case?
Negative?
Yes, and why is that?
Because the charge is negative.
I guess that's one
Or
way.
maybe it's the force, right? Does it depend on the direction of the force?
Does it depend on the direction? Oh, you mean for the direction of the electric field?
Yeah.
I guess that's not really a way I would think about it.
Mm-hmm.
And honestly, I'm going to be totally honest in this example and say that I am not 100% confident in conceptually saying, oh, it's negative, so it must be becoming more negative. Like electric potential, it's really hard to conceptually understand. I prefer to always actually go and calculate and go through the math. And that's how I always prefer to do it. And if we do the math, we'll get certain values. So let's go ahead and hop into the next part here. So we've gone ahead and we understand our electric field, what it's going to look like, and we know what our equipotential lines are going to look like. So now, quick little Gauss's law review from last week. What's going to be the x component of the electric field at point P out here? And then also, let's go ahead and not only calculate the electric field out here, Let's also go ahead and calculate the electric potential on the inner surface of our conducting shell here. And once again, as long as you can use Gauss's law to calculate the electric field at any given point, and then use our E dot dl integral, you can calculate the electric potential anywhere. Let's go ahead, let's take 10 minutes, and let's go ahead and actually do parts B through D here. So we want to go ahead and find the electric field, and then find the potential on the inner surface of the conducting shell, and then the potential at any point inside the shell, so between A and B here. Let's take 10 minutes, then we'll go over it. Also, welcome, Donald. If you haven't already, if you put your campus ID in the attendance form, that would be appreciated. Thank you.
What should I put my ID? Oh yeah, I think I already did it.
Oh, did you already do it?
Yeah, I already did it.
Okay, sweet. I actually don't have the form pulled up. I'm just assuming as people come in that they haven't already. If you already did it, good job.
Okay.
What was that?
No, are you still responding to someone question, or you don't? Because I have a question.
Yeah, go ahead.
So, I don't know. I have a question on class on the class. Call it. Wait 1 second.
Oh, the class questions?
Yeah, exactly.
We'll have time to go over a few of them at the end.
Okay.
Yeah, like probably around 2 o'clock, 2:05. But we're gonna go through this example, and then we'll have some time to go over stuff at the end.
Okay, by 2, you say?
Yeah,
By 2?
around there.
All right. No problem.
All right, so let's go ahead and go over these. So first thing we want to know is what's going to be our electric field outside of our conducting shell. How do we use Gauss's law to calculate our electric field out here? Well, first of all, what is Gauss's law again?
K Q enclosed over R squared.
So yeah, we can use Gauss's law to then find the electric field would be K times our Q enclosed over our distance from the center R squared. And how do we get our enclosed charge?
Find the charges. Just add up the charges that are within that surface.
And how do we do that? What do we know about our charges within our surface?
Well, the outer charge does not have a charge, so it's just the inner which we're given as charge density. So do we need to convert the charge density to some type of charge, or can we just
Yeah. So
use the charge density?
we want to find our enclosed charge as a function of our charge density.
Right.
I have a quick question.
Yep.
This class question of 8 is of today.
What do you mean for the assignments that were due on Monday or Wednesday?
Yeah, like what you do right now is that of a class question of the last Monday, or is of the last class question of today?
I'm doing unit 10 right now, which is electric potential, which, unless I completely missed a big change, that was this week.
Okay, so like what do you get that from?
What the electric field here? Or
no, like what do you get this question?
oh, I throw the questions together myself, based on the material you guys. Whenever I made this question, actually, this time last year, when I did SFAS for the class last spring.
Okay, so okay, I'm sorry. I thought you were doing the class question.
Oh no.
Okay.
Yeah, I stole the image from Flipit, but everything else is. I mean,
but like, are you gonna go over the class question?
Not specifically, but if you have a question about a specific class question, we can go over it at the end.
Okay.
Yeah. So how do we get our enclosed charge from our charge density?
Charge density times volume.
Yep. And what's our volume of our inner sphere?
What's just the volume of a sphere, right?
Mhm.
Not exactly sure what it is on top of my head.
It's in your formula sheet. You don't even have to memorize it.
All right. Yeah. I barely look at the formula sheet. But I don't know, like 1/3 pi r squared, maybe?
You're so close.
Pi cubed.
There you go. 4/3 pi. Then our radius cubed. The radius of our inner sphere is a. 4/3 pi a cubed. And then obviously we just plug that in up there, and we would get our electric field. So now, how would we go ahead and find our electric potential at the inner surface of our conducting shell? How do we solve our integral from infinity to b?
That's a good question. You said from infinity to b?
Well, I guess the first thing we want to know is, we know that our change in potential, delta V, from, we'll say, because we want to find it from infinity to b, is equal to VB minus V at infinity, which is the negative integral from infinity to b of E dot dl, right?
Yep.
And we know at infinity, it's 0. So essentially, our V is equal to the negative integral of E dot dl. How do we solve that integral?
We have to have two integrals that we might have to first calculate from infinity to a, then a to b. Is that what you're asking?
Yes, exactly. Well, not to a, but infinity to c out here, and then from c to b.
Oh, I see.
Yeah. But so we want to go ahead and break our integral into two parts. And why do we have to break it into two parts?
Get the right calculation.
What was that?
Because there wouldn't be a way to solve it with just one integral.
Mm-hmm. Yeah, there's no.
Or would help you get the correct answer.
Yeah. There's no way to solve our integral in just one step because the electric field isn't the same throughout our entire area. So we'll start from infinity to c, the negative integral from infinity to c of E dot dl, which ends up being our k times negative rho. I'm putting the negative here because our rho is negative.
Our density is negative, okay.
Yeah, rho and then 4 pi a cubed over 3r squared. And what is dl in this example here?
The direction of, right? Isn't it just a direction?
And if we're starting out here at infinity and we, for example, move in a straight line into here, so what is dl? What do we actually integrate here?
Nothing.
No, we're integrating something here.
Well, dl is the direction, the distance, right? So would it be r?
Exactly, dr. dl in this example would be dr, or it'd actually be dr, and then we have an r hat to signify the direction, but the dot product makes the r hat go away, because remember we also have an r hat here. So
just a quick question here. Is there a way we could do it from infinity to a, then from a to b?
Why would we want to go from infinity to a? Because a is the inner sphere. So we would have to go past c and b anyway to get to a, right?
Yeah.
So it's just easier to go from c and then c to b.
Okay.
Yep. And so that's our electric potential here from infinity to c. And then how do we get our electric potential from c to b? Well, we have our negative integral from c to b. What's our electric field inside our conductor between c and b?
0.
0. So what's the integral of 0 dr?
0.
0. So literally there's no change in potential between c and b. So our electric potential on our inner surface is actually the same as our electric potential on our outer surface, which we can go ahead and calculate here.
Oh, interesting. So
Yep.
if the conducting shell, if it's a conducting shell, then the charges at the surfaces are the same.
Or the potential on the
The
surfaces.
potential.
Yeah.
are
And
the
then
same.
that would also be the same potential between them, right? At any point from here along here.
Right. Interesting.
And that's actually the answer for part D. What's the electric potential at any point? It's always going to be the same.
Okay. Would this change if the conducting shell had a charge?
Well, obviously, that charge would mean our electric field outside is slightly different. But what's the if the conducting shell has a net charge, is there an electric field inside the conductor?
No.
No, there's still no electric field, which means the second part here is still 0 dr.
Right.
So there's still no change in potential.
Okay.
So now, how do we actually solve this integral? What's the integral of, first of all, let's go ahead and pull all of our constants out. We have k rho 4 pi a cubed over 3. What's the integral of 1 over r squared dr?
Excuse me, I have a question if you don't mind.
Yep, go ahead.
What's the infinity and the minus infinity represent? here, it's the infinity is a outward or it's the center of the sphere.
Infinity means we're an infinite distance away. Like we're all the way out here.
Away. Okay, so that means the minus infinity is
Oh, that's I
the
don't know.
center.
I don't know why there's a minus sign there.
Okay, good. So that's what I saw there. I was very confused.
Yeah. Yeah.
Okay,
Sorry.
okay.
Yeah. I don't know why that was there. We're gonna get rid of it. Goodbye. It doesn't exist. So how do we integrate 1 over r squared dr? What's the antiderivative of 1 over
So
r squared?
so so I think we integrate it with respect with your respect to r,
Yep.
right?
hmm
So I think uh k minus k minus k minus or 4 pi over 3. We can consider it as a constant.
Yep. Yep. And
Then
that's what we've done
integrate.
here.
Okay.
And so then what's the integral of 1 over r
So
squared?
uh, figure 1 square. To remind myself the.
Nathaniel, do you know what it is?
The integral of 1 over r squared.
Yep.
Then it just 1 over r, negative 1 over r.
Negative 1 over r, exactly. So it's negative 1 over r. We're going to go ahead and evaluate it from infinity to c, which obviously then we have a 1 over c, and then plus our 1 over infinity is just 0.
Yeah.
So it comes out to be negative k rho 4 pi a cubed over 3c. That's our electric potential at our inner surface and our outer surface and everywhere in between. And obviously we could go ahead and plug numbers in, but who cares about numbers except flip it, which is like half your grade in the class. But you guys can plug things into a calculator. So that's how we'd go ahead and calculate our electric potential. So now, what's going to be our electric potential difference? So what's our potential difference between our outer surface of our shell and the outer surface of the sphere? Let's go ahead and take 5 minutes and we'll go over it. It's actually also, let's do part F as well. So we want to go ahead and find the potential difference between the outer surface and our sphere, as well as the potential on the sphere if a net charge is added to our outer conducting shell. Let's take 10 minutes and we'll go over these.
Can you clarify why you use those specific bounds on your integrals?
From what, infinity to b?
Yeah, I know we
C.
said that between B and C it's the same, but is there a reason why we're using C?
So we use C because, actually, do I still have it copy pasted? Hell yeah. Okay. So, well, first we want to use from infinity to C because we're starting way out here at infinity. And we're going all the way in to C here. And then from C to B. And do you know why we start at infinity? Why don't we just start at A?
Because it's already defined as 0.
Exactly. We know it's defined to be 0 at infinity, so we're going to integrate from infinity to B. And to do that, we have to go from infinity to C, and then C to B, which happens to be 0. Does that make sense?
Okay, so we So we just use C because we were assuming we didn't know that it was 0 at first. Like, what would happen if we used B instead?
Well, the electric field isn't going to always be the same between those 2 points. So we know
Right.
what the electric field is outside of C. It's, KQ over R squared. And we know the electric field between B and C is different. It's 0. So
Okay.
yeah, so a convenient way is to break it up into 2 separate parts.
Okay, yeah, I see.
And you'd actually, if we did an example, like for part F, actually, we're going to have to go ahead and integrate from infinity to C, and then C to B, which, hint, it's 0, and then from B to A as well. And our electric field is slightly different between those 3 parts. So we have to break it up into those 3 parts.
Oh, to find a point A would have 3 integrals, essentially.
Yeah.
So, quick question. The electric field inside the sphere is also 0, right?
What, inside the sphere in here?
Yeah. Is that also 0?
No, it's not.
It's not.
It's not 0, but that shouldn't matter in these examples I'm giving.
Okay.
All right. So we'll take about 8-9 more minutes, and we'll go for E and F. So welcome, Sierra. Go ahead.
If the conducting shell was an insulated shell with like a uniformly distributed charge, would the surfaces still have the same potential?
Well,
like the inner surfaces?
would our electric field inside our shell be 0?
No.
No, so that means our E dot dl integral wouldn't end up being 0.
Right, but it's uniformly charged, so it would be constant, right?
No. I mean,
Wouldn't the electric field be constant if it's uniformly charged?
no, it would not. I mean, think of it this way.
Oh, because it's dependent on the distance.
Yeah, exactly. So, like, our electric field inside our inner sphere here is not constant, right?
Right.
Because we can use Gauss's law. We draw a Gaussian surface at whatever point we want to calculate, and our enclosed charge changes whether we're closer to the center or closer to the edge.
Yeah.
It's the same thing for if this were an insulating shell.
Right.
The enclosed
works
charge
with,
changes as a function of the radius.
Got it. So it only works with conducting shells.
Yeah, conducting shell potential is constant and the electric field is 0. But for insulating shells, it's not as simple. You actually have to solve the integral.
Yeah.
All right, so first of all, we want to go ahead and how would we go ahead and calculate our electric potential difference between our outer surface out here and our inner surface in here? So we want to find our potential difference between here and here. How do we go ahead and do that? Remember, same thing as before. We want to go ahead and break it into 2 integrals, right?
3 or 2?
Well, we're not trying to find the potential. We're just trying to find the difference here between C and A. From C to A.
So if we're finding difference, then we just have to find the potential of those 2 points and just take the difference.
Mhm.
But if we want to find the potential at A, we'd have 3 integrals.
But we don't have to do 3 integrals, though.
Right. No, I'm just saying if we wanted to find the potential
Yeah.
at point A.
Yeah.
So how would we find the potential at A, though? In this case, to find the difference, then we have to.
Oh, there's another sneaky little thing. Remember our definition of our potential difference from infinity to B, which is VB minus V infinity?
Mhm.
It doesn't necessarily have to be, one of the endpoints doesn't necessarily have to be infinity.
Can we see?
Yeah, so we can just have arbitrary points A and B, or in this case,
Right.
C and A. So it would be the negative integral from C to A of E dot dl. And so we break it down into 2 parts, right? From C to B and from B to A. What's the potential difference from C to B?
0.
0, exactly. Same thing we had before. Because electric field 0, potential difference is 0. So then we know that's going to be equal to the negative integral from B to A of E dot dl. What's our electric field? Is it the same electric field as down here?
Yep.
Yep, exactly. Same exact thing.
Different radius.
Yep, it's just different radius. Instead of integrating from infinity to C, we're instead going from B to A. I'm just going to do E dr because we know it's the same thing as down here. And then we know that ends up being K rho 4 pi A cubed over 3. And we evaluate 1 over r. What was that?
Is it going to be 3?
What do you mean? What do you mean 3?
Like the distance or the radius you are denominator. Is that going to be 3?
What are you mean, the values or?
No, the distance.
From what to what?
It's From A to B. I'm just asking why it's a 3.
Oh, why the 3 down here?
Yeah.
Oh, that's the volume of our
Oh,
of our
4
sphere.
thirds.
Yeah, 4/3 pi a cubed.
Oh, okay.
Yeah, sorry. Your wording got me a bit confused. But so, right, we have our integral, and then we evaluate from B to A, because we don't have any point where it ends up being 0.
Yeah.
So that ends up being, so we have our negative K rho 4 pi A cubed over 3. And then we have 1 over A minus 1 over B, right?
Minus 1 over A, minus 1 over B.
Yeah. All right. I just pulled this negative sign
Oh.
out here, by the way.
Okay.
Yeah. So we have 1 over A minus 1 over B. So that's our potential difference from our outer shell here to our inner surface. Does anyone have any questions?
Sure. How about don't we need to calculate the potential energy between B and A? Like a B, like a B and then the outer between B and outer surface of the sphere.
That's what we just did. We just calculated the difference between B and our sphere. That's what this is
okay.
here.
Okay.
Yeah. Because
And
we didn't have to calculate the potential V at the 2 points, then subtract them, because we can just use our integral to find the difference.
okay, but how about between the center between A and then the outer surface of the sphere.
What do you mean from here out to here?
No.
Or
No, from there to the center.
oh, we're not worried about getting to the center here. The question's just asking to the edge. But if we wanted to calculate it to the center, we just have to. What the hell is my? I think my headphones are about to die. What is going on? Okay. Anyway, but we would just have to do another integral from A to the center, from A to 0, and
to 0.
and we'd have to calculate what our electric field is on the inside.
Okay, I got it.
So now, part F, if we want to go ahead and actually add a charge of, 0.5 microcoulombs, or we'll just call it a charge Q. If we want to add a charge Q to the outer conducting shell, what's going to be our new electric potential VA on the outer surface of our sphere of charge? First of all, this is the part where we would have to use 3 integrals. Right, Nathaniel? So how would we go ahead and break that up?
So we're adding a charge to the conducting shell.
Mm-hmm.
Okay. Electric field is still 0.
Yep.
But what is the new electric potential at VA?
Yep.
Well, Q enclosed would change for 1.
For if we're calculating the electric field, Q enclosed changes for which parts? In here? Or out here? Or both?
Out there.
Yep, exactly. So our electric field is going to change when we're outside the conducting shell. Inside, it's still the same.
Right.
And so, what would be our new Q enclosed when we're outside?
So our new Q enclosed would be our charge density, which is just PV plus our new conducting shell charge.
Yep. So we'll call it, negative rho 4/3 pi a cubed plus Q. And we could actually calculate with numbers, but who cares?
Yeah.
So negative 4/3 rho pi a cubed plus Q. And so then go ahead.
So now that we have that, we can calculate the electric field for the outer surface.
Mm-hmm.
Which is, K for density.
Yep, K times Q enclosed, which is Q minus 4/3 rho pi a cubed over R squared.
Mm-hmm.
And we have our R hat. So then, we want to actually plug things into our integral, right? Our E dot dl.
Yes.
What are we integrating from?
So we want to first integrate from infinity to C, right?
Yep.
Then we want to integrate from C to B.
And what would that end up being?
0. There's
Yep.
no change. Then we want to do B to A.
From B to A. And we've already done B to A, right?
We've done B to A and nothing changes, so we can just use that.
Exactly. So we can just use this down here and plug it in up here.
Yep.
And so we go ahead and calculate our integral from infinity to c.
Mm-hmm.
Right? It ends up being k q minus 4/3. Let me actually go ahead and it's negative. Remember, we have all these negative signs. Negative integral. So then we have k q minus 4/3 rho pi a cubed. And then we have our integral of negative 1 over r,
Mm-hmm.
right? From
Yep.
from infinity to c.
Mm-hmm.
So it ends up being, we have our 1 over c, and then we have I'll just throw the negative sign out front.
Will become positive then.
Yeah, I'm taking the negative sign that was in here and I threw it out front. Does that make sense?
Right.
Yeah.
Yes.
Or, wait,
Well,
hold up.
Yeah, it'll be positive, right? Because
Yeah, it'd be positive.
negative.
You're right. Negative signs cancel out. And then we go ahead and add our part from down here. So we have k 4 rho pi a cubed over 3 1 over a minus 1 over b. Just add them together. Boom. That's our answer. Anyone have any questions about this? And obviously we could go ahead and plug values into a calculator, but who cares about that for an example? Only
This
Flip
was,
that cares about that.
Yeah, I'm just saying that this was really helpful.
Thanks. Donald, you had a question about a class question you wanted to go over, right?
Is it okay if I take a screenshot real quick?
I'll post this in the session docs.
Are you gonna post it like along with the question?
Yeah. The questions are posted in the session docs already.
Oh, I kind of wanted to take a screenshot, like side to side. Just
Of
to see
the paint document
the pain and the question, like,
And
side to side, like what you have right now.
right here.
Yeah.
Go ahead.
You just zoom out a bit.
Yep, sure thing. Is there? Hold up. Zoom out. Oh, there we go.
I can take 2 screenshots. Okay. Got it. To the left a bit.
Mm-hmm.
Awesome.
Also, if you want to see these again, they'll be in the session docs.
Okay.
Should go ahead and save that while I'm thinking about it. Donald, you had a question from the class questions you wanted to go over, right? All right. He's missing his opportunity.
Yeah, I also want to go through the class questions.
Yeah, I got time for one real quick. I've got class in half an hour though.
Okay. So question 4, I think same question, don't know if there's questions.
Did you post it in the session text? Or at least like, so I can see it, because I actually don't have access to the class questions.
Oh, like a picture of it?
Yeah.
Interesting, okay. I'm just tempted to do it, so hopefully. Alright, one sec.
Alright. Wait, hold up.
Let's see that.
Let me see this. Oh, oh.
So that's the second part. You want to open
Open the first part. Okay.
yeah.
Didn't open that. Yep. So we have sort of the same example, except we have R, 2R, and 3R. What's your question?
So for part 8, it's asking us to determine which electric potential to use. I chose the difference between 2 points, right? Because we need to know what infinity is, or at least we need to know 1 point is, and we can use infinity for
Mm-hmm.
the difference. Is that correct? Well, I think so. But like the question is kind of been hard to understand, but I was hoping that's what I was asking.
So in this question here, it tells you that for one, you are. Is there a way I can actually draw on this? Hell yeah. So it's asking you to find the potential at the center,
Mm-hmm.
and perhaps is there any way I can? So it's asking you to find the potential at the center, and it's
Right.
telling you that the potential at infinity is 0.
Mm-hmm.
So you're calculating the potential at a specific point, which by finding the difference between that point and infinity.
By finding the difference. You said?
Yeah. So you use the
So-
difference from infinity to the point to find the potential at the point, because you know the potential at infinity is 0.
Right. So what's the answer for A then?
I would
Because we need
guess.
to find the difference, but you also said we need to find it at a specific point.
Well, the A is just asking determine if you are calculating the potential difference at a specific point or the difference between 2 points, and he's just asking you to say find it at the center.
Okay, so at a specific point. Okay.
Yeah.
Okay.
Yeah, you're just
so my-
overcomplicating it a bit.
Okay. So my other question is on the second page.
Mm-hmm. Ba-doom.
So we just went over this, so pretty sure this is correct. Right, because it's a conducting shell, it's 0 within the surface of the shells. And the Q enclosed would always be Q naught because the outer shell does not have a net charge, but the distant, well,
Mhm.
R squared is different.
Yep.
So I'm sure that's correct. Below, where it's asking us to find the integral, I'm assuming at this point we would actually use the volume. No, the E would be. Oh, so this it's also correct. So that integral part for the first one, would that be correct?
So from infinity to 3R,
Yeah.
so K times Q. Well, so this is the electric field. So K times Q. Is that
Q naught.
Q naught over 3R squared?
Yeah.
So it's K Q naught over R squared, and then so you evaluate it. So the KQ comes out. So we have KQ comes out, and then we find negative 1 over R evaluated at infinity and 3R. So
Mm-hmm.
is Q not positive or negative?
Q naught is positive.
Positive, okay. So we have our negative sign would come out here. So we have 1 over 3R. So it's negative, so it's negative KQ over 3R minus our kq divided by infinity, which would be 0. So it'd be negative kq over 3r.
Let's see.
You were close. You just essentially you forgot to bring the negative sign from integrating 1 over r squared.
Right. I see. Okay.
And then we also it's not r squared because r squared becomes negative 1 over r singular.
Right. I need to integrate before I use the radius. Of course.
Yep, exactly.
Okay. Then I can do the rest.
Yep.
That should be easy.
The rest is really straightforward.
The last one is asking us to find it at the center. So simply, this is kind of what we did too, right?
Mhm.
But with the center be at 0. Right?
Yeah, I would assume.
Okay, so just add the integrals.
Yeah, exactly. We just add all our integrals up.
Yeah. Okay, thank you.
It's pretty straightforward. Just break it down step by step. And
All right, thank you.
calculate. Yep, sure thing. Thanks for coming, man.
Yeah.
See you around.